So Nikhil Chitnavis is our team member from the CFD team of FOSSEE. He's also a final year student of PhD. He's doing PhD in IIT Madras. So he's a very experienced person, and the next demonstration session will be handled by Nikhil. So over to you, Nikhil.
So this session has been taken by Ranjit sir, and he demonstrated and explained the application of CFD in the water sector. So we'll continue with that only. So we'll go. I will going to demonstrate a few cases how we can model it in open form. So first case which we're going to see, and Ranjit sir has also talked about it in his session, that is dam break model. So it is already given in the open form. If you go to open form, let me show you also where it will be, where you can find it. So in my case, it will be in some different location, but you have to go to tutorial section in the open form. And I'm using OpenFOAM 2412. Inside the tutorial, there is one multiphase folder, and inside multiphase folder, this interform you can see, and there are lot of flow parameters which is given, like laminar flow, ranks, modeling, and LES. So we'll see with some basic case of dam break in the laminar flow model. So this case we can simply copy, and it will be good that you should not run any case in this installed directory or folder. It's better to copy it in some other location. So coming to this dam break case and this session also. So we're going to see the two-phase flow using VOF model. So in VOF model, we'll actually trying to capture the interface of the two phases. So for the current case, I'm using air and water interface, air and water as two fluids. So we're trying to capture the interface between the two fluids. So starting with the setup. So this I will not go into much detail, and these things have already covered by Ivan in the previous session. Starting with zero folder, which consists of the boundary conditions or the variable, that is the pressure and velocity. Apart from these two variables, for the multi-phase flow, one alpha is nothing but the phase. It will one additional variable it will going to solve, and the additional equation also it will going to solve. Then coming to constant, which consists of the parameters of the fluid, which has density, viscosity, and even the information related to the mesh and system folder, which consists of the controlling parameters of the solver, what discretization scheme we're going to use, and the metric solver. So this is the first case, which is called as the dam break model. So this mostly has been used to study the behavior of water column when, or the application of dam break, when the dam will break, how the water will going to behave, how much instability it will going to form. So you can see, so to simulate this, we, as I've already said, this is the established case in open form. So this is the water column, which we're going to initialize in the open form, and the remaining blue section is the air domain. So under the effect of gravity and also the density, how the this water column will going to behave and how the flow will be there. Further moving forward, as I've already said, this is a VOF model, which is used for solving the multi-phase flow. And these are the governing equation which it is solving, starting with the continuity equation and momentum equation. So if you look in this momentum equation, one additional source term it will going to solve. So as we are solving the two different fluids, so one is the continuous fluid, which is water. So surface tension will come into effect, and this surface tension force will treat it as a source term in the momentum equation. And to capture two different fluid and their interfaces, This is the alpha equation or the phase equation. So the alpha is denoting the phase of two fluids or two fluid domains. So this alpha equation is the additional equation which this interform solver will going to solve. And to capture the interface between the continuous phases of fluid, this convective term has to be discretized using a different discretization equation, which we're not going to cover into detail. So coming to our dam break case. So this is the setup, which I've already said zero constant and system. So if we'll go inside the zero folder, as I said, it will consist of pressure and velocity. And apart from this pressure and velocity, one additional variable you can see, which is called as alpha. Alpha is the phase. So we're going to see one by one in all these three files. So in these files, we are defining the boundary conditions, which we are defining on the wall. So as you can see from this image, these three walls, I have given the no slip boundary condition. That means the velocity at the wall will be 0, and this is open to atmosphere. So same thing we can see from here also. So left wall, right wall, and lower wall has given a no slip boundary condition, and the atmosphere, that is the top wall, has given the pressure inlet outlet velocity, and that means it is open to air. Further, we are seeing the 2D case. So that means, so if you see this image, so these are the walls, and on this wall, I'm giving a no slip boundary condition. So how to define no slip boundary condition, and what is no slip? So no slip, nothing is means the velocity at the wall will be 0. That means the fluid will going to stick on the wall. So either we can define simply a no slip, or we can define a velocity on this wall as 0. So for that, we can also write fixed value, and we can define the value of the velocity as 0. So we are defining, sorry, no, so I write uniform. So like this also we can define the no slip boundary condition. That means we are instructing, or we are implementing that the velocity on this wall will be 0 for all the time step. Or the second way, we can simply write the no slip, which already this boundary condition has already been coded in the open form. So both ways, in using both ways, you can define the no slip boundary condition. Apart from this, the top region, I said it is open to atmosphere. So because of this, I am defining pressure inlet outlet velocity. That means it will not going to restrict the flow. It will simply allow the flow to move out of the domain. Also, these default phases, that means the front and back phases, which I will going to show when going to develop the mesh. What exactly is this default phases and why we are defining it as empty. Now coming to pressure, so you can see in the pressure it is written pressure RGH. So RGH is nothing but we are subtracting the rho GH term from the pressure. So in the multiphase flow, we're going to define the gravity also as a source term in the momentum equation, which I've showed it here also. So this is the gravity term, which is act as a source term again in the multiphase flow simulations. And what boundary condition we're going to define it here. So on these three wall, we have defined some fixed velocity. Even though it is a 0 velocity, but some fixed value we have defined on the wall. So pressure will be the gradient of that means the fixed value will in the CFD field. If you are defining some fixed value to any boundary, it is called as Dirichlet condition, and the other variable should be go as a Newman condition. So it will not, we are not providing any fixed value. Based on the time step and based on the calculation, it will going to recalculate it or back calculate it on each of these walls. And again, as I've said, atmospheric condition, it is open to atmosphere. So that's why we are defining it here. The pressure is 0. So it will take it as a gauge pressure. So it is open to atmosphere. Now coming to alpha phase, that is the water phase or gaseous phase. So here we are simply defining, because we are not defining any phases on the wall. So that's why we have given 0 gradient to the boundaries. And again, it is open to atmosphere. So whatever, if it that means it will allow the fluid to go out of the domain. Now coming to mesh or the boundary or the computational domain. So as this is a established case in the open form, so block mesh or the mesh file is already been given, which you can see that vertices have been defined. Block mesh, and also the block mesh is worked on dividing the computational domain into various blocks. So based on this, you can define the number of vertex in X and Y direction, and it will create the mesh for you. And here in the boundary section, you have defined the various boundaries or the patch name for the boundary based on the vertex. Based on the vertex, you have defined it here. So we'll see how it is going to create the mesh. So for this demonstration, I'm using OpenFOAM 2412. So first I will source it. Then I will go to that location where I've kept that test case. Now, as I've said, we will require a 0 constant and system. So what is this 0 org? So this is simply a original file. So whatever changes, if you want, you are doing in 0 file, and if you want to check what is there in the original file, so it's like a backup file for the boundary condition. So you can simply make a 0 folder out of this simply by copy paste and rename it as 0. So now this will become act as boundary condition, constant and system. Now we will going to create the mesh using the block mesh. So for creating the mesh out of block mesh dict file, so the command is block mesh, and yeah, so it has created the mesh, and you can see it is reading all the patches also, which we have defined it in the block mesh dict file. Now to check the mesh, whether or the property of mesh, whether it's a orthogonal mesh, how many mesh elements are there, how many faces are there, that we can see using the check mesh command. So after running this check mesh command, we can see the total number of cell is only 2268. So it is very coarse. You can refine it here by editing the block mesh file also. Then other thing also you can check what is the aspect ratio of the mesh, whether the mesh is orthogonal or not. Those things you can modify and check it using check mesh command. Now to visualize this mesh, we have to create a temporary file which can be readable in ParaView. So I'm using this command touch. You can give any name and then .foam. So this is our computational domain. And if you click over here, this surface, one option is there, surface with edges. So it will give you the, you can visualize the mesh using this command or this option. So this is our computational domain. And as I was mentioning, that we are not going to solve it as a 3D domain, it is a 2D domain. So that default phase is empty, what we have defined it here. So that means this front face and this back face, we have defined it as empty. So it will not going to solve on these two faces. That means it will not going to solve any equation or any parameters on these faces. So which will treat it, this domain as a 2D domain. Now coming to, as I've showed it in this, about this water column. So till now, there is no water column, or we have not initialized anything. So how we're going to initialize that water column, and how we're going to differentiate that which part of this domain will be treated as water column and rest of the thing as air. So for this, inside this system folder, there is one dictionary or file called as set field. So here we're going to initialize the various phases. So this is the file in which first we're going to define the default field. So here we are considering the default field as air. So alpha phase will going to vary from 0 to 1, where 0 denotes the fully air domain and 1 denotes the water phase. So all over the domain, I am defining it as alpha is 0. So by defining this, it will going to initialize air all over the domain. Now coming to the water column. So it is nothing. So if you see, the water column is nothing but a rectangular box. So for which I'm defining a box with the dimension. So this dimension you can get it, means what is the exact size of this domain. You can check it in parallel also, or the size of the domain you have already defined in the block mesh dict file. So if you come here, so it will show you what is the exact size of the domain. So based on this domain size, I'm defining the box for the water column here. So this will be the so in this initialization also, it will work as I'm defining only two vertex, so it will diagonally place it. So this will be the first vertex, and this will be the second vertex. So based on this, after reading these two vertex, it will going to form a rectangular box. So that's why we are defining here the two vertex only, and the field value in this box, I'm defining it as a alpha is 1. So as I've said that alpha is the phase and 1 denotes the water phase only. So using this file, we're going to initialize our flow field. So to initialize it, and also if we'll see the alpha water file that is there in the 0 folder, currently the internal field is 0. That means nothing has been initialized. It is taking a default value of 0. But once initialization will be done, you will going to see some values it will going to show, and also this thing we will going to visualize it in parallel. So to initialize, the set fields command is there, and after using this command, you can see it is saying that the alpha value of 1 has been initialized to this box. Now if you'll see the same file, we have to reload it. Oh, so this file belongs to the 0.org. So we have to see this file. Yeah. So now instead of internal field as 0, you can see some values it has defined here, starting with 0 and 1. Also, the same thing we can visualize it in Paraview also. So if you load this file in Paraview again, yeah. So now in this drop down box, all the parameters are visible. And if you'll select alpha water, so now you can see it has initialized this water column and the remaining is air. Now for the simulation of this dam break case, we are using the interform as a solver, and the controlling and discretization, you can check it using these files, starting with control trick, FE scheme, and FE solution. So we're going to see quickly one by one all these files. So FE scheme will going to tell us that we can see the equation. So in the momentum equation, which term is discretized using which scheme? So the first one is the temporal term, this DDT term. Second one is convective term, then gradient of pressure, and then the diffusive term. So all this term we're going to discretize using different schemes. So this DDT scheme is the first term, that is the temporal term, which and all this discretization scheme is already given in this open form. So that's why we are simply calling this function by the respective name. So this DDT scheme is the first term, that is the temporal term, is discretized using Euler discretization scheme, which is the first order implicit in nature. Then the gradient scheme is the discretization of the pressure, which we are discretized using Gauss linear. So in this, in open form, Gauss linear simply denotes the second order central difference discretization. Then coming to divergence term. So as you can see, there are various divergence or convective term, both are same. So you can see there are various convective term has been defined. So why they are defining this 4 divergence term? So you can see the first divergence term will be coming from this momentum equation. Now this is also a divergence term, which is coming from the continuity equation, and this is the third term, convective term, which alpha equation will going to solve. So because of this, there are different divergence or convective term, and which are discretized using different discretization scheme. Now coming to Laplacian term, which is the diffusive term. So this is this fourth term, in which the viscosity of the fluid is defined. Then coming to the FE solution. So each term, that is alpha, pressure, and velocity, will form a matrix. So how we're going to solve this matrix, using which solver or which iterative method we'll use for solving this matrix is defined here in this file. So we're not going into detail of this matrix solver. So we can simply say that it is something like we have already know the different metric solver, starting with Gauss-Seidel method, conjugate gradient method. So these things are all only defined it here. Now coming to the control dict. So in control dict, we'll going to call our solver, that is interform. We're going to define that the simulation will start from what time, and we can also change this time. So as we are initiating the simulation, that's why we have defined the start time as 0. End time we can define. So we are running this whole simulation for the total time of 1 second with the time step of 0.001. So this delta t also we can keep as fixed, or it will going to vary based on our simulation. So that's why they have defined as adjustable. Not going to be remain constant. It will going to vary as per the convergence. Now coming to write interval. So after every 0.05 second, it will going to write, or it will going to save one file as a data file. Now in which format we are saving our data? So that we have defined it here, that is the ASCII format. You can save all your data, or you can save the files in the binary format also. Now current number, we are defining it here, that is the maximum current number. So if we are defining the maximum current number, so the simulation or delta t will going to calculate based on this maximum current number. So this is the basic overview of this dam break case. Now we'll going to run this using interform solver. So I will simply write interform, and if I press enter, it will start running. And as this is a very coarse mesh, so it will not take much time to complete our simulation, and it has already completed also. So as I've said, based on the write interval, that it will going to save after every 0.05 second. So we can see that at the interval of 0.05, so this is the first file, that is 0.05 second. Then after each and every 0.05 interval, it has saved these many files. So after the completion of this simulation, we can visualize it also in the para view. So for that, we have to refresh it so that it will able to read all these time steps. Now you can see instead of showing 0, it is showing the maximum of 19 time steps. So to see the animation of this dam break case, we can simply play it, and you can see how the dam breaks and the behavior of the water. So this is how it will going to behave after the breakage of this water column. So that only I have showed it here in the animation form. So this image you can save it also using this screenshot option, or you can form an animation using this save animation option. So it will give you a lot of option whether you want to save each and every time step as a PNG file, so that many images it will going to save, or you can directly export it in the MP4 format. So if I'll save it, it will ask for whether I want this transparent background or not, and it will start saving. And this animation you can use it for the later purpose also. Now coming to the velocity, so this is only showing the behavior of alpha phase. Now how the velocity will going to behave? So simply we have to change from alpha water to velocity or pressure. So which will going to show how the pressure and velocity variation all over the fluid domain. Further, uh, you can see the streamlines and velocity vector also in this by taking a slice. As it is a 2D domain, so no need of taking slice also, but it's better to take it. So there is an option called a stream tracer. So if I'll switch it on, so you can see a line. So it is denoting that it will going to plot the streamline across this line. Either you can use this option or which is the default, or you can change the location of this line. And if I apply this option, you can see some streamlines it has formed. Yeah. And you can change the density of this streamline. So there are various options given in this stream tracer option. So you can see the maximum length. If I'll decrease the maximum length, it will decrease the length of the streamline given here. Also, the number of time steps or maximum steps, if I'll increase, it will increase the density of this. Apart from this, if I want the streamlines in some specific areas, so we can use this seed type. So earlier it was line, now I'm changing it to point cloud. So if I want streamlines in this region only, so I will go to point cloud. A point cloud, if you see, will appear, and I only have to move this point cloud to that specific location. And if I apply, it will give me the streamline at that location only. And after that, I can increase the maximum length to further crowd that area. Also, I can increase the radius of this point cloud, which is given here. So if I define it as 0.1, you can see the radius of this sphere will increase. And the streamlines will be more visible. So like this, you can control the streamlines also. Further coming to the post-processing. So you can define some probe location in this flow domain to observe the dynamics or the instability of the flow domain. So this was all about this first case, that is dam break case. If you have any question, then you can ask. Otherwise, we can move towards the second case. Okay, so Aditya, related to the y plus value. So first, you have to calculate the y plus value. There are many online tools, sites available to calculate the y plus value. And in the block mesh option, let me show you. So in the block mesh option, so currently I've given the grading as 1 1. That is that means it is a equal spacing between all the cell, all the mesh elements. So by changing this, you can vary the y plus value or the grading also. Yes, we can apply the grid adaptive technique also in this open form, which is called as adaptive mesh refinement, AMR. We can use, but for the VOF technique, solid particle, this thing will be little difficult. But in case of VOF method, But for this kind of modeling, you can use Eilerian approach, where you will not able to capture the interface, but as a bulk effect, you will able to visualize it. And this kind of approaches has been widely used for boiling or even for fluidized bed kind of thing. So in fluidized bed, there are two phases we used to define. That is one as a solid particle, bed of solid particle, and other as air or water. So that tutorial, one basic tutorial is already being given in the open form that you can explore. So we can start the second case in the demonstrative session. So the first case which I've showed was the well-established case given in the open form tutorial. The second case is the modeling of wave, which I'm taking from the case study repository of the FOSSEE. So that case, you can find it in the case study section. If you'll go to FOSSEE website under open form section. So under this completed case study, you can check this. Yeah, you can check this case. In this also, the solver used is open form. And in this, it is shown how to model the wave and how the interface between the air and water will going to behave. So you can simply download it and go through it. And meanwhile, I will explain all about this test case. So this test case is case number 129. So this test case I have already downloaded. So we can go through this test case one by one. So let me show you. So this test case is something like this. The bottom wall is no slip condition. This red zone is the continuous water zone. The blue one is the continuous air zone. From inlet, we're going to define a wave type boundary condition, which we're going to see how to define it. And this is the outlet condition. And again, the atmospheric condition is open to atmosphere. So this is the computational domain, which I've showed just now. So coming back to the test case. So again, in this zero folder, these three files will be there: velocity, pressure, and alpha phase file. Second will be the constant folder, which will consist of G, that is the gravity, transport properties, and turbulence properties. Now, apart from these three files, one more file you can see, that is the wave property file, which we'll going to explore after a few seconds. And polymesh file. So the polymesh folder will consist of all the details of the mesh, starting with boundary, phase, neighboring elements, and the number of points which are available in the mesh. And the system folder. So coming to the zero folder, we're not going to spend much time on this zero folder because most of the thing I've already explained in the previous demonstrative session. But I was talking about we're going to model the wave, which I've already shown a schematic of the wave in this slide. So at the inlet and outlet, instead of any fixed value velocity, here we have defined the wave velocity, and this boundary condition is already been compiled in the open form. And what all parameters we're going to consider, we'll see. Then at the outlet, again it is wave velocity. Now the back is nothing but the back and the ground. Ground is nothing but this bottom one, where I have defined the no slip boundary condition. So that's why instead of giving the no slip, we can define the fixed value as 0. Now the top, as explained, is open to atmosphere. So that's the pressure inlet outlet velocity is defined. Now, similar to velocity, wherever we have defined the fixed value, we'll define the gradient of pressure at that patch. So that's why this fixed flux pressure is defined. And on the top wall, we have defined the pressure as 0. Now coming to the alpha water. So in this file also you can see in the internal fields, the default value has given us 0. That means it is not yet initialized. And apart from that, here also at the inlet, the wave alpha, that means using the pre-compiled boundary condition of wave alpha, it will going to take some value for implementing the wave condition. So this was all about the boundary condition. Now coming to the constant, we'll see one by one all these files. Out of which three of these files, that is transport property, G, and turbulence property was same as that was given in the previous case. So in this we have defined G. So there are three, as G is a vector quantity, so that's why Gx, Gy, and Gz we have given here. So the actual geometry is in the Z direction, so that's why the gravity is defined in the Z direction. And the other two values is given as 0. But it depends on you whether how your geometry will going to be. It can be you can define gravity as per your geometric detail. Now coming to transport properties. So as I've said, in the transport properties, the viscosity and density of each phases will going to we have defined, or based on the fluid requirement you can change it also. But for this case, the two continuous phases are air and water. So the transport model we have defined as Newtonian. Nu is the kinematic viscosity and rho is the density. Similar to this water phase, for air phase also we have defined the kinematic viscosity and density. Now apart from these two parameters, sigma is the surface tension of the fluid medium, that is the water medium. So we have defined it here. Now coming to turbulence property. So the simulation type, as I've showed in the earlier case, that we can do this kind of simulation using Rans modeling for laminar also and for the LES. So this simulation is performed using laminar model. Now coming to the wave properties, which is actually being used for implementing the wave inlet condition. So you can see here it is reading we are defining the inlet patch. Now on which phase we are going to define the wave motion. So that's why we are defining alpha as alpha water. Now there are various models based on which the wave nature will be dependent on. So that you can explore further. Yeah. So coming back to this wave modeling case. So how the wave property will be dependent on. So there are various wave models which you can further explore. If you simply type wave properties open form. So this user guide wave modeling, you can check there are various models given here. So you can do trial and error kind of thing, how the wave will going to behave by using different models. So for the current case, we are using Stokes one wave model. Now, wave height we have defined here. So how it will going to decide the wave height? So after the initialization, uh, suppose this is the half h by 2 height. So from here, how much it will go up and down, that we have to define, not from the origin, but from uh, the interface. So that height we have defined. Ramp time is nothing but after the start of simulation, after how much time it will going to start implementing this wave type boundary condition, and what is the total time period of this wave. So all these things we have to define it here. And similar to that, in the outlet, we are simply defining that it will allow the wave to go out of the domain. Further, uh, in the system folder, these things I have already explained what is control drift, FE scheme, and FE solution. And similar to this, first we have to initialize the two phases in the set field dict file. So here also, the default phase we are defining it as 0, that is the air phase. And then here we are defining a box, and in that we are defining that the continuous phase will be water. So using this set field, we are only distinguishing the two phases, but not the wave. So wave initialize will start using that. Wave modeling will start to implement using that wave property to boundary condition. Further, the earlier case I have showed was using a single processor. This case we can see how we can run any case using a multiprocessor. So for that, the decomposed pardict file is available. So in this, we can define the number of processor or number of subdomains. So here I have defined 4. So which means the whole geometry or the whole fluid domain will be divided into 4 subdomain, and each processor will going to solve only that much fluid domain. And based on the system, you can increase or decrease this number of fluid domain. Also, instead of running all the command one by one, we can keep all the command in a single file, and that file we can use for reading or we can use for the simulation. So you can see for decomposing the domain, we are using this decomposed file. For initialization, we are using set field file. Then for running the simulation, so this get application, that which means as I've showed, let me open the control dict also. So here we are defining the solver name that is under the application, which is the interform. So it will going to call this solver using this get application command, and as we are running it in solver, parallel, so you will going to see 4 processor folder it's going to form, which I am going to show. So once the simulation will be over, we have to reconstruct. Reconstruction means we have to get the information from all the 4 or 5 whatever subdomains you have divided your fluid domain or fluid section. So we have to take the information from all these processor and clubbed into one. So for which we are using this reconstruct par command. So for running this now, instead of writing all the command in the terminal, I'm simply using this all run file. So as you can see, this file is already been given. So for running this file, /all run, if I'll press enter, you can see it will start showing which command it is running. And as I've said, that we are dividing this whole fluid domain into four separate subdomains. So that's why these four processor files it will going to create. And inside each processor file, it will going to solve for all the time steps for that much fluid domain. So once it will complete, I will show how it will going to behave. Also, you can see that some log files it has created. So you can see using this log.enter how much time or how it is running in all the iterations you can visualize it here in the terminal. So for that, you have to write this tail -f. You have to call this file, and if you press enter, you can see all the iterations which are going on. So as it will take time to complete the simulation, so I will only run it for a few more seconds, and after that I will show the animation which I've already prepared. Better to stop. So now if you'll see, I've interrupted the simulation in between. So it will not going to run that reconstruct par command. So if you are interrupting this whole process in between, so you have to manually write this command reconstruct par. So it will take the information from each of this processor file and create a time step outside of this folder. So for now, if you'll see, only 0 folder is there and no other time step is visible, even in this also. So once I will start reconstructing, you will able to see it has started reconstructing all the time steps. And here also you will able to visualize it. And this time step only we are going to use for the visualization in Paraview. So once it will be completed, I can visualize it in Paraview. Yeah. So after the completion of this reconstruct part, now we can visualize it in the Paraview. So as I've said, we have initialized this fluid domain using the set field file. So that's why there is, instead of showing any wave implementation, it is only showing the two phases. And we're going to implement our wave type boundary condition using that wave property file. And in that wave property also, I have defined the ramp time. That means after 0.3 seconds, that boundary condition will going to implement. So you can see from here that at 0.1, we are not visualizing any wave in this domain. Even at 0.2 seconds, we cannot see, but at 0.3 second, you can see some depression is coming, and then it will start to implement the wave. Yeah. So now you can see some sinusoidal variation is coming in this interface, and that's how we have implemented the wave. So anyhow, it will not going to move further because I have not run this simulation for enough time. So I can simply show the animation. So if you'll run it for the enough number of time steps, so this kind of wave behavior you will able to visualize. So this was all about the second case. If you have any question, then you can ask. Okay, so decompose power means we are decomposing the whole fluid domain into different subdomains, and reconstruct power means uh, whatever we have solved into different processes, we are reconstructing it into single time step file. Yeah. So for further clarification, we can visualize all the.
Hello.
Yeah. Hello.
Actually, I have one question.
Yeah.
In the constant file, as you have said, the wave height that is related to the first means initial height of the
Yes, sir.
water.
Yes. Initial height of the water. Yes.
Okay, thank you. Acha, wave period means this is imposed.
Yes.
Okay.
Yeah. So I was saying that we can visualize the all the fluid subdomain. So the file we have created here, right? Fluid dot form for the visualization. So if we'll simply copy this file inside this individual processor, we can visualize the. So you can see if I'll compare. So I have divided this whole fluid domain into 4 different subdomains. So this is my whole fluid domain, and this is a one part of it. So the processor 0 will going to solve only this much part till here. You can compare it. So this is the whole idea of decompose thing. So you can see it is only solving the 1/4 of it, which will speed up your simulation if your total number of mesh elements are very high. I hope this is clear. Okay, if there are no further questions, you can explore this test case, which is already available in the case study repository of FOSSEE.
Nikhil, are you done now?
Yes, I'm done.
So we can take up the questions now as well. And we were
Okay.
thinking of holding a simple tutorial case so that people who are new to OpenFOAM will at least understand a bit, just a
Yeah,
basic,
that will be
like an ICOFOAM case.
Yes.
So for people who are facing any issue or have not understood anything, you can ask us your questions. Then once that is cleared, we can move ahead with the simple case.
Okay, so for this, Aditya sir, so for letting the wave to go out of the domain, for that only we are defining the outlet boundary condition, which I can show it again. So here in the outlet, we are defining the wave velocity as 0, and this wave velocity will going to read all the properties from this wave properties. So here in the outlet, we are simply defining alpha water. So that means it is allowing only the wave to go out of the domain. So it will be better to download this case and explore. And if some doubt will be there, you can ask. Okay, it seems like even no other further questions are there.
So if there are no more questions, we can wind up. Okay. So see you all. Thanks a lot for joining today.
Thank you, ma'am. Thank you.
Thanks. Bye bye.